In this video, I wanted to walk you through some of the stuff we had been doing in class. As our test problem, we're going to work with sort of the distribution of pets that people own. All right, so I looked up some data and I found this approximate distribution, and we're going to assume people only own one pet. That is certainly not true. Maybe later on we can talk about, what if you own more than two pets? What is the probability it's a dog and a cat, or fish and a bird, and stuff like that. But for now, what we're going to assume is that each household just owns one pet. And so the question is, which pet is it? All right, so let's sort of work through a lot of the concepts that we've been looking at in class. So for starters, here goes the distribution. And so if we want to draw a PDF of this distribution, right, so we'd have dog, cat, fish, bird, right, and so forth. We do our standard sort of, bar chart graph. This goes up to 41. Cat goes up to 30, right? Fish 10. Bird less than that, right? And so we'd see something kind of like this, right? This would correspond to our PDF. Right. So now let's do a few problems that we've sort of discussed in class. So I think one of the standard problems that we asked was, what is the probability that you own, let's say, a dog, given that you own a mammal? Okay. So this is one of the problems we did. And so the way we'd go about calculating that is by finding what is the probability of owning a dog and owning a mammal. Okay. Divided by the probability of owning a mammalian pet. All right. So this is that special case we talked about. Or is it? Nope. Actually, it's not. I take it back. We'll solve the opposite problem, and that will actually be the special case we talked about. But let's sort of work through what we end up getting here. All right. So we're asking ourselves, if you own a mammal, all right, which is either a dog, a cat, a rodent, or a horse, what is the probability that it's actually a dog? Okay, so I tell you, Bobby owns a mammal. All right, what is the probability that the mammal that he owns is a dog? All right. So we go ahead and do our conditional probability equation, right? And we can start with the top. All right. So what is the probability that you have dog and mammal? So these are actually kind of subsets of each other, right? We know dog is a subset of mammal. Right? So if we look at our state space, here we have mammals, right? And here we have the set of dogs, right? So if we do dogs and mammals, then effectively we're only interested in the probability contained within dogs. If you can't read my handwriting, that in fact says dogs. All right. So what is the probability that's over this whole space, right? Over the whole sample space, how much of that probability is contained in dogs? Well, we have that, right? It's actually 41%. Okay? So this quantity right here is going to be equal to 0.41. Right. Now, the next quantity we have to calculate is the probability of mammals. Okay? So we mentioned there's 1, 2, 3, 4 different types of mammals. Right? Mammals account for a large fraction of the pets, and we can figure out what fraction that is by adding each of their probabilities. So here we want to add 41 plus 30 plus 5 plus 2. I think that gives us 8, and then 78. Okay? So what that tells us is the probability of mammal, that if you own a pet, it's a mammal, is 0.78. So now that we know the numerical values for the probability of dog and mammal, and the probability of mammal, then we can say the probability of owning a dog, given that you know the pet is a mammal, is equal to 0.41 divided by 0.78. All right. So if you're ever on an exam, that's sufficient for me. You don't need to calculate that value there. That's fine. All right. So let's ask a different question. So just for fun, we're going to ask, what's the probability that your pet is a mammal if given that it's a dog? Okay, so logically, you should know if you own a dog, then your pet is definitely a mammal. Right? And so this was that special case we had talked about, right? Where we said if B is a subset of A, right? And we're trying to calculate the probability of A given B, that's just equal to 1, right? So again, it's kind of logical here if you think about it. Given that you own a dog, what is the probability that your pet is a mammal? That's equal to 1. Right? And the way that we can always do it mathematically, so we ask ourselves, what is the probability of dog and mammal? Now we calculated that up above, and we're going to divide that by the probability of dog. Right? And so again, this probability of dog and mammal we know from up here, right, which is 0.41. And then we divide by the probability of dog, right, which is 0.41. Right? So sure enough, 0.41 divided by 0.41 is 1. Now, I think doing all this math is a bit of a wasted effort, because you should recognize right away that if you own a dog, it's a mammal. Right? Now, I told you there are some cases where sometimes it's easier to calculate probability of A given B faster or easier than the probability of B given A. So hopefully in a later video I'll give you an example of that. But for now, here goes just a simple example of using conditional probability with these pets. All right. Now in lecture today, folks kind of started glazing over when I wrote the following notation, where I said, give me the sum of the probabilities for all the x that are in some set x. All right, so maybe I could give you a more sort of applied problem according to these pets. So an example of this is, give me the probability of all animals that are in the set of mammals. Okay. And I want to sum the probability of each of those animals. Okay. So in this case, all we're doing is we're going through each of the animals that are mammals and summing up their probability. So that would be equal to the probability of owning a dog, plus the probability of owning a cat, plus the probability, what else? Of owning a horse and a rodent. And I'm just going to write this on the next line. Right. So of course I can just add these numbers up. I get 0.41 plus 0.30 plus 0.05 plus 0.02. I don't know what that adds up to exactly. Or do I actually? I do. It's 78, right? Because we did that before. So if you add that up, it's 0.78. So what you see is this is just sort of a shorthand notation, right? We're talking about elements within a set. So here, our set X was actually the set of mammals. While X is just an animal, right? So hopefully that brings some clarification of why I was writing the sum of probabilities in this way. All right. Now, it's a bit different. So let's say we had a weighted die. So normally we talk about dies having even probabilities. But let's say we had a weighted die where you could get a 1, 2, 3, 4, 5, or 6. And maybe it's weighted in a way so that instead of being, 1, 6, 1, 6, 1, 6 all the way down, it's something like 0.5, 0.1, 0.1, 0.1, 0.1, 0.1, right? So this is a seriously weighted die where you're way more likely to roll a 1 than you are any other number, okay? So now if I ask you, what is the probability of, let's say, X? So X is a random variable representing a die roll, okay? So you roll the dice once, or die once. I think singular is die. So what's the probability that your die is odd? Okay. So I can write that by saying the probability that the die is odd is equal to the sum of X that's in the set of odd numbers. Right? And then P of X, right? So that would be equal to the probability of 1 plus the probability of 3 plus the probability of 5, right? And then we just go in and add that up. So 0.5 plus 0.1 plus 0.1 equals 0.7. Now certainly, I could write that the probability of X is odd. I could also write that as the sum of X equals 1 to, actually I could just say, oh, how would I write that? Trying to think of something sneaky. I could say x equals 1 to, this is kind of a weird way to do it, but you could do it. 1 to 2 times the probability of 2 times x minus 1, right? So here you'd plug in x equals 0, x equals 1, and x equals 2. So that would give you probability of 2 times 0, oh, plus 1. Sorry, that should be plus 1 plus the probability of 2 times 1 plus 1 plus the probability of 2 times 2 plus 1, right? And that would give us, you know, again, what we expected, the probability of 1 plus the probability of 3 plus the probability of 5. So now I'm asking you, what's easier to write? Is it easier to write some funny summation, right, like this? Or is it easier to write a summation over a set, right? For me, it seems like it's easier to write a summation over a set. And so that's why I like using this set notation, right? We're going to sum over all x numbers that are odd numbers, right? The sum of all numbers x that are in the set of odd numbers, right? And that way we just plug it in, 1, 3, and 5. So this is one reason why I like using sort of set notation when we do probabilities, especially when probabilities are for more complicated events, right? If I just ask something like, what's the probability that x is equal to 5? Okay, that's easy. Or if I ask something like, what's the probability that x is greater than or equal to 4? That's pretty easy, right? That's not too bad, right? Because then we could write it as a summation, x equals 1 to 6 of p of x, or 4 to 6, sorry, of p to x, right? That's not too bad. But in life, you're going to run into cases like this, right? Where it's not a specific number that you're interested in calculating the probability, but some weird set, right? And so this is why, again, I like using set notation when calculating probabilities, right? So again, if we ever want to calculate the total probability over a set, you're welcome to use the set notation if it makes sense, or you know, if it's a simple problem like this, where you're saying what's the probability that x is greater than 4 or less than 3, right? Where you're going to go over a numeric range, a set numeric range, like 4, 5, 6, where you increment by 1, then yeah, use this notation here. Right? You can do either way. It's both correct. But you can certainly see in some cases, it would be odd to do. It's not exactly easy to write or clear what you're trying to do in this example, right? But again, these two guys, right, are the same. They give you the same answer, right? They both give you the sum of the probabilities for 1, 3, and 5, if you will.